So how's everybody doing? Doing good? Cool. Okay. So I'm talking about cracking Wi-Fi. I'm sure that all of you have done something like that. Have a lot of people here cracked Wi-Fi before? Any sort of web or WPA or anything? Yeah. Okay. Cool. So yeah, I'm going to talk a little bit about how to crack Wi-Fi and how to crack it on hardware. So one of the things you'll learn today, hopefully, unless you've messed with FPGAs before, is how you can use custom hardware in order to crack stuff really fast. And so I'm actually giving a talk similar to this at Black Hat this year called Faster Phoning Assured, and we kind of coined this new acronym up there for FPGA. So first to start out, I'm going to give a quick intro on FPGAs. So people, have you ever heard of an FPGA before? Anybody? Oh, okay, cool. All right. Has anybody seen me talk about this before? Okay, all right, cool. So it'll be a really quick intro. I'm just going to skim over it. If you have other questions about how the hardware works, just feel free to ask at the end. Yeah. I'm going to go over CowPatty, if anybody's used that before. Go over how WPA works and give you a brief intro into how it's able to crack it. And then also talk a little bit about pre-computing tables, so you can do all of your computation ahead of time and then use it kind of like a rainbow table later on. And I'm also going to get into some performance stuff, how fast you can do it on your computer and how fast I can do it on customized hardware. Then, if anybody's ever played with Airbase or heard of that before, it's a set of tools written by Johnny Cash, a friend of mine, and so I'm going to go over some of that stuff and how I've modified it to hook into hardware and crack stuff a lot faster. Then I'll just have a few notes then on to tie everything up. So the real quick intro into FPGAs is basically it's a chip with a ton of general purpose logic. So you've got ways to do ANDs, XORs, standard gates. You can do flip-flops and registers. You can do block RAM, which is kind of similar to the cache on your processor, where it's a really tiny RAM that's SRAM based, so it's extremely fast, and it's you have just tiny little ones on the FPGA itself. Then there's also DSP-48s, which are basically really high-speed multipliers. And with those, you can do like 18 by 18-bit multiplies at 500 megahertz and really fast. And you get a bunch of those on the FPGA. You can also do accumulators and adders and all that kind of stuff with those general purpose blocks. And then there's also DCMs that let you take a clock from an external source like an oscillator and then step it up or step it down to whatever frequency you want. So with this sort of general purpose logic, you can make just about anything that you can think of, and with the three things on the bottom, you can kind of use it to optimize your code and get it to run faster with the hardware that's on there. So quick intro into FPGAs. This is actually a top-level view of a Vertex 4 LX25. And Vertex 4 is made by Xilinx. There's the main competitors out there are Xilinx and Altera that make FPGAs. There's also a few other ones out there that are kind of smaller fish. But we use the Vertex 4 LX25 for one of our cards. And when you look at this, you basically have a bunch of input-output blocks, which are actually tied to pins on the FPGA that get hooked up to your bus or whatever sort of peripherals you have hooked up to the actual chip. And on the package, they end up getting routed over to these different input-output blocks that provide various things like you can set some things like how much drive strength you want when you're sending output to a pin, like how many milliamps you want to provide out to it, what sort of IO standard you're supporting. You can set it to do like LVDS and other sorts of IO standards, and all that's programmable on the FPGA. So there's a lot of really cool things you can do just programming the different pins for doing different things. And also, right in the middle is where all the clocks come in, and so make sure to put all those right in the middle because you want your clocks to feed out to like almost everything on the whole FPGA. So they have really fast routing resources for your clocks to go everywhere and trigger all your flip-flops and stuff. Then you end up with a bunch of slices, which are general purpose, small little things with your XORs and registers and all sorts of things in there. And like on the LX25, you end up with about 10,000 slices on the whole device. And you can configure those and connect them all together to make whatever sort of logic you want. Then you have DCMs, which are your clock multipliers, and they're kind of located on the top and the bottom of the input clocks. And those actually have fast routing resources to go out and trigger pretty much everything on the FPGA really quickly. And then there's a few rows of block RAMs, just scattered different areas, so you can hook up to those. There's 72 of those on the LX25. And there's a row of DSP-48s, so you can do really high-speed math. You can also build them together to do like FFTs and different sorts of cool DSP algorithms really quickly. And then Xilinx has a programmable routing matrix that basically connects every single component almost to every other component somehow. And there's tons of layers of interconnects. And so really, like, you can have something on one corner that connects directly to something on the opposite corner, and it just kind of handles all the routing and stuff. So you can build whatever you want. Any questions about FPGA stuff at all? Okay, so introduction to WPA. This is kind of a thing that I downloaded off of Google. So basically, normally with WPA pre-shared key, if you used that before, you type in a passphrase. It has to be between 8 and 63 characters long. And what it does is it takes your passphrase and it runs it through this pdkdf2 function. And it's a pretty standard way of hashing stuff. It's actually in one of the RSA specs, the PKCS2 or something like that. 5? Okay. So yeah, you basically run it through this function, and it ends up creating a PMK, which is essentially a hash of your password that actually gets used for like all of your WPA stuff. So I'm going to drill down into the pdkdf2 function a little bit. So with WPA, they end up running SHA-1 HMAC about 4,000 times to generate the first 20 bytes of the PMK. And then they run it through another 4,000 times to generate like the last 12 bytes, if that makes sense. And normally I think that the PKCS5 or whatever recommends that you run it at least 1,000 times, and so they just chose 4,000 to make it nice and clean or something. But inside of each SHA-1 HMAC, you're basically looking at running a SHA-1, with your key XOR with a certain value inside of another SHA-1. And so it ends up translating to basically doing like a SHA-1 init, doing an update with your master key, which is your passphrase you type in. And then basically taking, the T up there is your SSID, so it's also seated on your SSID. And then, so you basically, throw in your master key, throw in your SSID, and then run a final, and then take the state of that, which is basically the output, and then feed that into the next one down, I guess, here. So the output from this one is fed into there, which is just the same thing as calling this function and then feeding that output into here. And so, so it actually requires quite a few SHA-1s for each SHA-1 HMAC that you're trying to run. And one of the cool things is that because the state after this update over here and after this one are going to be always the same throughout each SHA-1 HMAC, you can actually cache the state value and these different state values, and then just start up with that when you're running through each HMAC. So it's an optimization that you can use to speed up the process. So each HMAC, you're only actually doing like 2 SHA-1s versus 4. So that's one optimization that I use to speed it up a little bit. And so essentially, as long as you can try a passphrase, you feed it in through this algorithm, you get a hash out, then you can run it through the same sort of stuff that's used to like seed your temporal key and stuff like that, and then actually compare it with network traffic that you receive. And if all the hashes match up and the packets look about the same, then basically you know that you've gotten the right key. And if they don't match up at all, then you know that you've gotten the wrong key. So it's really a brute force attack where you try all the different passphrases that you want to try, and then whichever one matches is the right one. So with CalPatty, I modified it and implemented the whole SHA-1 and PDKDF2 step in an FPGA, and currently uses 8 SHA-1 cores. It uses block RAM to buffer words fed to the cores. So I kind of set up a ring buffer sort of thing in there, so it actually makes sure that all the SHA-1 cores are getting values like immediately after they finish. So it's nice and clean. And basically, as long as your PC is able to supply enough data to it, like by the time that it gets through the queue or whatever, then you can actually utilize the cores entirely fully, so there's no like extra clock cycles in between them. It's really efficient. And basically how it works is the computer talks to this buffer, and it'll load in like basically the kind of like the state that SHA-1 should start out with, and then it kind of does the rest of the work. And it loads it into a bunch of different entries into this array here. And then once it gets to the bottom, then it actually fires off the core. And so then, like the first 8 values go to the first 8 SHA-1 cores, and those start choking away at it. And then once those are done, it moves on to the next 8. And then the PC notices that, oh yeah, it's done with that, so it kind of goes and fills in these. So the basic concept of the ring buffer is that as long as you stay right behind where it's at, and then you basically have like this huge buffer down here that it can run through, and as long as you kind of stay within that, then you make sure that all of them are utilized. If that makes sense. So performance comparison on like pretty crappy P3, you can get about 25 a second. On a 3.6 gigahertz P4, you can get about 60 a second, like just running on your PC. Opteron, about 70. Intel Core Duo, we tried it on one of the MacBook Pros, and that got about 70 per second. That's actually like 35 on each core. And Aircraft, it's a little bit better. I think they have some sort of optimizations for like Animax or SSE2 or something like that. And with the FPGA on one of our little compact flash cards, I can pass it around later if you want. It's a little compact flash card, and it gets about 430 per second. So that's a slight improvement, about 6 times faster or something like that. And we also sell clusters of 15 of our compact flash cards. You can get about 6,500 per second. And we have higher end ones that will get maybe around 1,000. So it's a bit faster just running the hardware. Yeah, so one thing that we wanted to try and do was pre-generate a bunch of tables of like huge word lists for the top SSIDs. So RenderMan emailed me a while back, and he was like, "I've got this huge passphrase list of ones that I want to use, and I've got a list of the top 1,000 SSIDs from Wiggle.net. So I want to compute all these tables for all this this huge data set." So he gave me this 1 million word passphrase list, and one thing that was kind of funny is that I guess that the passphrase list is actually it's got 430,000 words from Kevin Mitnick that Kevin Mitnick used or something for hacking people, and some of the other ones were derived from Google hacking or like Webster's dictionary and stuff like that. So it's kind of funny. So RenderMan had a cluster laying around like a bunch of lab PCs, and he managed to compute this set in about 1 month using this cluster. And then he found out that every word in the word list had a return character in it. So I don't know how many people put return characters in their SSIDs and in their passphrases, but if you do, then RenderMan can own you. So it's been a month, and then he was pulling his hair out, so he emailed me asking for help. And on one of our 15-card clusters, I did it in 2 days, like about 48 hours. So it's a bit faster. I'm going to do a quick demo here. And he just kind of wrote a quick curl script to just run cowpatty a bunch of times, so that's why I put curl in there. Have people cracked WPA before? Anybody in here? Oh, okay. All right, I'll do a demo of cracking WPA then. Hopefully we'll have enough time for this. I'm just going to make sure that it's set up here. So I've just got like this D-Link access point set up over here, and let me make sure I'm connected here. Okay. Yeah, and I'm connected. So I just downloaded Auditor the other day, and I'm a total like wireless script kiddie when it comes to like using all the Linux tools and stuff. So if I stumble through this, please forgive me. Okay, so I'm just going to up the interface and set it into monitor mode.
Can you change your contrast some to visible different?
Oh, sorry about that. Yeah. Oh, that doesn't help. Whoa. I'm not into this Linux thing too much. Okay, well, there's the settings, font, huge. Better?
Yeah.
Alright. Think that'll work? Okay. Yeah. And then I'll, let's see. This one's far easier. Alrighty. So let me see if I can find my access point. I think this is the right one. I'm sure some of you are already trying to associate with it or something. Okay. I think this is me over here. So. So it turns out that when you're cracking WK, you actually have to capture the whole authentication. So the easy way to do this is to inject a bunch of deauth packets to force the person off the network, so they have to reassociate, and Windows will automatically reassociate without even telling you. So it's all good. So there's this AirForge program. Let's see the MAC address here. So, and you just put in the MAC address of access point. And then the card, the client you want to deauth. And then you create a PCAP packet out of it. So. All right. Now I'm going to switch this view over so you can capture the auth packets. You like my one-handed typing skills here? What's that?
Move the mic on the table.
He's doing great. Okay. So now we should see some packets show up if I'm doing this right. Might help the packets a little bit. Let's try the packets. Something going on. Oh, actually, I'm going to log that too. Okay, well, looks like this is working for some reason. I think I'm on the right channel. Okay. Well, I think I've got another capture I can use, but maybe I can just type it in. Oh, I think I want to go with the second one. Yeah, okay. I'm just putting the, I think this is the right card. I've got two cards in my laptop, so. Oh, there we go. Okay, cool. Glass again. Yeah, there we go. Perfect. Well, let's see if this is enough for cracking it. You have to catch enough of the authentication or to crack it. So let's save this out. I'm just going to stick it on the USB key, crack it on the machine. It's nice to freeze up here. It's nothing to teach or something. Yeah, let's start this over again. Okay. Okay, well, I think it's trying to auto-mount something or something. So I'll just go on with the rest of the presentation, and I have another demo later, so I'll finish this up when it gets to that. Okay, so one cool thing that we found out was that in OS X, there's actually this utility that you can just run airport if you know where it is in the path and stuff. And actually, you can generate your PMK from this. And so Beetle found this out actually at layer 1, and he wrote a little Perl script that actually does the same functionality as CowPatty, just calling this little utility. So if you want to do CowPatty in a few lines of Perl, you can play around with that. It's really slow though. That's getting about 10 passes per second off each core of its laptop. So. Okay, so Airbase. Airbase is it mainly consists of basically Johnny a long time ago built a distributed web cracker, and so it actually has a daemon and a client for doing the distributed web cracking stuff. So you can have like a whole lab of PCs that just brute force web, and that's called JC Web Crack. And then he also re-implemented AirCrack, and it's a cleaner interface, and he's got a bunch of code reuse between the two. So he's built this whole framework called Airbase for doing like packet injection, building packets. He has a whole library for farming out keys. So essentially, like if you're using AirCrack and you only have a few interesting packets, and you just want to use the statistics that you have and then use it to brute force the rest of it, then you can actually do that distributed, and we're working on support and trying to get it so, like with FPGAs, you can string a bunch of them together and use it for that sort of thing. So he's got a bunch of different tools for manipulating PCAP files, like just sending out PCAP files to the air, messing around with stripping the prism headers and recalculating checksums and things like that, so things work properly. He's got a bunch of different tools in there, so you should check it out sometime. JC AirCrack has most of the stuff that you get with normal AirCrack and AirCrack NG. And it looks pretty similar to the normal AirCrack, and he's implemented all the normal statistical attacks, and you can tell to use only certain ones and stuff like that. So it's pretty cool. And JC Web Crack is what I've modified to get to work with our cards. So basically the server looks like this, where you fire it up with a PCAP file and say like you want to crack 40-bit web or something. And then you just have a bunch of clients connect to it. So they can be normal clients connecting with PCs doing all the work, or with like one of our compact flash cards doing the work, like in this case. And it basically just farms out different chunks of the key space to different clients, and eventually, they go through it and find it, kind of like distributed.net stuff. So, eventually he wants to basically have everything tied into airware, and so AirCrack can, farm out stuff and be able to transparently offload it to hardware, and you wouldn't really. So pretty much everything plays nicely with hardware. And eventually it'd be kind of cool to have like other support for other weird types of hardware like GPUs or whatever, but that would be pretty difficult. Right now our client just consists of, all you have to tell the FPGA is like a start key, where you want to start in the key space, what your stop key is, like how far you want to go into it, what the key size is, if you use it 40-bit or 104-bit, and what the PRGA is. So you find a packet and you just decrypt the first like 6 bytes. You send that off to the FPGA and the amount of key space you want to search, and then it just tries all the keys in that space and compares the PRGA, and whichever one matches, is the right key. So then there's other things to see if it's busy or if it's found keys, stuff like that. And this is kind of this whole higher level view of the suite and stuff. How I implemented it in hardware is I've got one mode that uses 32 cores, which is basically 2 sets of 16, and that one gets about 6 million keys per second, and the 48 core one gets about 9 million, but you need to have some cool cooling behind it. So I'm actually demoing this on a card with a heatsink in my slot over there, so I can show you that later if you want. And it uses block RAM for the S-boxes, so it's basically this really small state machine built around block RAM for all of RC4. And it just tries every key between start and stop. some optimizations that I've done with RC4, if you're familiar with it, is running it in hardware. All you really have to worry about is you basically just have like a key as an input, and then you want to provide some sort of output, which is your PRGA. So how the whole thing's set up is the computer will say like, here's your stop, here's your end, and I'm looking for something with the output PRGA bling, for example. And it'll actually be a bunch of like bytes and stuff, but just for example here. So the RC4 key generator will talk to an RC4 core and say, okay, you're using, you should generate a PRGA for key 0, you should generate a PRGA for key 1 and 2. And then they return back, like their PRGAs, and then it, kind of feeds off the next ones to them, and they feed back to the PRGAs. And then this one comes back with the right PRGA, which is bling. And so then it's like, oh, okay, the key is 4. Or whatever that was, yeah, 4. So pretty simple. How I optimized it was, there's this whole initialization step in the beginning of RC4. And on the FPGA, if you're actually going to be writing out the permutation of the block RAM, it takes forever. Because all you're really doing is writing out like 0 to address 0 in the block RAM, 1 to address 1, 2 to address 2. And you don't want to waste time doing like stupid stuff like that. So the first optimization I thought of was I could have basically like one block RAM that kind of feeds pairs of block RAMs. So like in the first stage, this one will be initialized as 0 through 255 or whatever, and it'll just write out all its values to like ROM A, and A over there. And then when it's done doing that, then RC4 will use that initialized block RAM because it's all initialized with permutation, and it'll start using it. But then as it starts swapping around values in RC4, then that's going to become dirty, and so it's going to need to be initialized later. But then the cool thing is that then it can switch over to using the other block RAM, and that one's all initialized because it's done in parallel. Well, it's running on the other block RAM. So then it just kind of goes back and forth between two, and that works fine. But I came up with a better optimization for this. Because block RAMs can be addressable up to 32 bits. Basically, you can configure it to be like an 8-bit, 16-bit, or 32-bit. I chose to configure it as 16-bit. And because in the KSA, when it swaps values in the ROM, it actually ends up going through and writing to every individual. It's guaranteed that it will write to every individual value in the ROM. And so, for example, if you do a read and you're only using the bottom 8 bits for your actual data for RC4, you'll read back some values. And then when you go to write, all you do is you set, like, say, the top 8 bits to whatever your address is. So right now it's writing, when it writes to address 2, it writes a 2 into there. When it writes to address 54, it writes 54 in there, and so on. And then what you end up having is, at the end of the whole RC4 stage, at the end of the KSA at least, you'll end up with values in block RAM looking like this. And then all you do is, like in the next stage, in the next RC4 run, you just swap over, so you're using the top half, which is already initialized to all of your initial values, and then you start initializing the bottom half, and so you just swap between them that way. And so then it only requires one RC4 core or one block RAM for your RC4 core. So that's kind of one optimization that I'm using. And yeah, so you just kind of work off the top half and then switch between the two. So there's some cool little tricks you can play with hardware to try and get higher performance out of things. So this next demo, it looks like this is good. So I'm going to finish up the demo for the WPA stuff, and then do this RC4 one, and then wrap things up. All right. Anybody ever have problems like this with Ethereum? Yeah? see where I'm spinning up. There we go. I think I've got another capture that I can use. So. All right. Nice to reboot this. Okay, so I'm just going to use this other capture that I captured before. I think this should work. So basically, you just run cow patty, and you supply it with a dictionary file. So I've got this dictionary file, and give it a packet capture. I think this one should work. Tell it the SSID, and tell it which FPGA to use. Actually, let's do it without FPGA. So it's cracking away. We just went through 100, 200. I'm going to stop it because it'll take a while. So I'm going to basically tell my FPGA to reboot to use the cowpad image. I just have this little script that does it. And tell it to use FPGA 0. So now it's going through at about 430 per second. And, oh, I'm going to find it. That's weird. I don't think any of my demos are working today. This might be a bad PCAP file. Yeah, I might have to throw it in. Oh, let's try this one. There we go. Let's try that one. All right.
You can just change your SSID and send the email file.
Oh! All right. Yeah. All right. Yeah, sorry. The one-handed typing here. So this one should work. All right.
Why is it stopping at D?
What's that?
It's stopping at D, so there are new words.
Oh yeah, this is just a small dictionary. Yeah. I think that. Let me try the other dictionary. There we go. Okay. So now I have the right dictionary. I think one of them might have had return characters in it or something. So okay, so that's basically how it works. As long as it has the right password in there, it'll find it and it does it really fast. There's also the GenPMK option now for CalPatty, where you can create a hash table of basically combos of passphrases and hashes, and then you can just scan through it really quickly later on when you want to crack stuff. So I'm just going to demo that, just so you can see how to use it. It's pretty much the same usage as CalPatty. Let's see, dump, FPGA, and then you just output a hash file. So right now it's just building like basically a Berkeley database of passphrases to PMK values. And then you can just go into CalPatty and you can specify your hash file and your SSID and let's see, your capture. And there it goes. It did it at about 30,000 passphrases per second because just everything's pre-computed. And on a decent computer with a faster hard drive, you can get it in the hundreds of thousands range. So that's basically how you use it once you pre-compute stuff. And actually, I've got the tables that we generated, and I'm going to give them away later if there's any good questions. So I've got 6 copies of that if you want to play around with that. Now for web cracking stuff, see how we're doing on time. It's 11 o'clock p.m. I'll just demo the stuff here so you can see it, just in case the caption doesn't work. So I'm going to swap it over to the web cracking core. So now it's reconfigured for web cracking. And I think one of these will work. Yeah.
Try to make it quick and wrap up.
Okay, yeah, no problem. So I built this Perl script that just fires off a bunch of screens and a bunch of daemons, so this one should work. Yeah. Specify how big it is. So right now it's firing up a JC WebCrackD, and it just spawned a couple other screens that are actually the clients. And so there's some cool matrix effects involved, just for style points. And since there's 2 cores on the card, each one of these screens is attached to one of the cores, and each one should be going at about 3 million per second, and it does about 6 million total. So per card. This is going to take a little while to complete because I think the key is a little high. So I'm going to switch over to the other thing and finish up the presentation. I can show this to you later. So performance-wise, JC WebCrack on a normal computer, like a G4 will run about 150,000 per second. On my P4, you get about 300,000. And on one of our cards, you can get up to 9 million if you have good cooling. On a cluster, you can get up to about 135 million. If you want to spend a ton of money and buy 5 for our clusters, you can crack 40-bit web in about 13 minutes. And, or SSL if you want to build software for cracking that. So the conclusion is, get an FPGA and start cracking. If you run across anything like reverse engineering where it's like, oh man, they're using some weak encryption thing, but it's still, like 50 bits that I got to brute force or something, then FPGAs are a pretty good way to go for cracking things that are somewhat weak, but strong and too strong for your computer to crack it. So, just finished. Cool. Yeah. So yeah, I just found the key. It was 0011223344. And yeah, make use of hardware to create crypto. Realize that you can do really fast stuff with hardware. Add full matrix ASCII effects when possible, because they're just cool. Choose bad passwords. And the hardware that I'm using, that's our compact flash card. It's got like a bunch of RAM, ROM, gigabit Ethernet, and you can get it with a PowerPC if you want. It's basically a full embedded system. It might be the world's smallest supercomputer, if you want to call it that. We sell 15-way clusters of 15 of our cards. If you're interested in trying to crack stuff.
Can you tell us what these things retail for?
Okay, well, right now with this card, we're selling it for about $2,700. The cluster is about like somewhere around 30 or 40 grand, I think, or something like that. So if you want to crack 40-bit web in like 13 minutes, you're going to spend like maybe about 250 grand or something, at least for this hardware. At Black Hat, we're actually going to be presenting on cheap crack, which is a way to brute force DES keys really quickly with cheap hardware. So the basic idea is that there was deep crack back in 1998 that the EFF built, and so we're just re-implementing that with today's FPGAs and making it so you and a bunch of your friends can go out and buy, like a couple FPGA boards each and spend a few $100 and just chain together all your resources and crack 56-bit DES really fast. So a couple greets, Johnny Cash for building Airbase, Josh Wright who built Cowpatty, Renderman for getting me to do the PMK stuff, Beetle who made Ghetto PMK, and audience, you can throw fruit at me now if you wish. And any questions for free hash tables?
Yeah. What kind of language should we program the hardware?
Oh, it's all in Verilog.
Verilog?
Yeah. You want one of these?
Yeah, sure.
Okay, cool. Go ahead.
What are the advantages of having a PowerPC chip on your blog?
What are the advantages?
Yeah.
Well, okay, so like if you have really complex state machines that are a lot more suitable for software, then the PowerPC is great because it's really difficult to build logic that can run at 450 megahertz and like handle full instruction set and stuff. So some of the other cool things you can do with the PowerPC is because it's inside, like in the middle of the FPGA, you can build custom instructions. So there's a set of a few extra instructions that actually can trigger logic on the FPGA. And then your logic has full access to all the registers, so you just read in whatever and write out. So you can have an instruction that does like DES or SHA-1 or whatever. It's pretty cool. Go ahead.
Does your PowerPC core
If you want one of these, you can come up and get one. Yeah.
your PowerPC core is on the FPGA itself, or it's
Yeah, it's on the FPGA itself. It's built into the die. On our little compact flash cards, you can get at least one of them on there. We also have a card bus size card that you can get dual core on it. So it'll come with two 450 megahertz PowerPCs inside the FPGA. And if you want one of these, you can have one. Anybody else? Is that it? Oh.
Yeah, what would be the frequency crypto accelerator, like on the shelf for like $150? Because pretty much the generic processor, the certainly like it's an accelerator or something like that, only one all
You're wondering how it would perform if you used like a crypto accelerator? The main problem is that with the bus interconnect, like actually talking to it, sending it your challenge and getting back the response and stuff, it's just that the bus ends up being the main limitation. If you can keep all the key generation and cracking on the card, then you just get massive throughput. Like when I crack landman hashes, I'm doing about 375 million keys per second. And so if you look at that times 8 bytes for your hash, 8 bytes for your output, that's a lot of bandwidth you're looking at. Like tens or hundreds of gigabytes of data off of a little compact flash card. So even though even though on an ASIC you're going to get a lot faster performance than an FPGA, there aren't really ASICs you can buy out there that are geared specifically for cracking stuff, unless you maybe have any friends with NSA or something. If you want one of these, you can grab one. Any other questions or? Okay, cool. What's that?
How much hardware do you know to do with it? I mean, it's pretty, well, of course the cards and stuff, but to program the FPGA.
Yeah, the language is pretty simple. You just have to get your mind wrapped around everything being in parallel. But the language is really simple to pick up. And then you have to just play around with the tools for a while to figure out how everything works and ways to optimize things. But I don't really have any electronic engineering background or anything like that, so yeah, if you're just a software person, you could probably pick it up fairly quickly. Yeah, so you can pick up 2 of these if you want. Anybody else? Oh, yeah, back there.
Just you guys want to play with this briefly, you were on if you use yourself, you when you did figure out if you were not kind of doing all the work. Yeah, now it's your product for
Are you talking about Icarus or? Yeah, Icarus is pretty cool. I don't think you can actually build the full files for programming FPGA, but yeah, it's a lot faster than the tools, the commercial tools out there for just testing things and simulating things. Yeah, so Icarus is a good one. On Xilinx's website, you can download a free 60-day trial, and so just set your clock ahead like 10 years or so when you install it, and then it lasts for 10 years. There's also some good things on Altera's website, so lots of good tools out there. And yeah, if you want one of these, you can grab one. I've got one more left if there's any other questions. All right, who wants one of these? Okay, whoever can get up here the fastest then. All right, thanks a lot, guys.